My name is Professor Crothor O'Brothy. I'm the head of the School of Engineering, and it's my great pleasure to introduce this evening's inaugural lecture by Dr. Doug Baney, our Honorary Visiting Professor. And the title of the lecture will be Illuminating Our World, the Ubiquity and Versatility of Lasers and Interferometers. Doug is Worldwide Corporate Director of Education for Keysight Technologies, based out of Santa Clara in California. His experience spans over 30 years in microwaves and photonics technologies at Hewlett-Packard, Agilent and Keysight Laboratories, with more than 90 academic publications and seminars and 240 patents. That's really impressive. He was responsible for more than £500 million in value generation through technology innovation. He led the technical team which invented the first mass-produced laser-based optical mouse. He was general co-chair of the Optical Fiber Communications Conference and received the highest technical distinction of Fellow of the International Electronic and Electrical Engineering Society. Since he was appointed visiting professor in 2020, Doug has been actively involved in efforts to improve the test and measurement capabilities of the School of Engineering's Electrical, Electronics and Engineering EE teaching and research labs to make them more competitive on a global scale. And we've done this in partnership with Keysight Technologies, and certainly I know the opening of the new labs will be held in the autumn, and that's certainly something I'm looking forward to. This state-of-the-art test and measurement equipment allows students to work with the latest industry standard equipment, providing them with the skills and expertise they need to excel in their field. Doug has also re-established our partnership with Keysight's Edinburgh Laboratory, which will allow the school to stay up to date with the latest developments in communications and signal processing technologies. Moving forward, Doug will work with the school to develop research programs in areas of advanced measurement to further breakthroughs in the field. Promising areas include human-machine interface advancements, taking advantage of the latest developments in AI and electronic test kit. And Doug will also continue to work to advance the teaching laboratories in coordination with Dr. Daniel Chitness and the academic staff from the EE discipline. So Doug, over to you.
Thank you. Thank you very much. It's an absolute honor to be here at this great school. And I know COVID slowed us down for this lecture, but now we're here, and hopefully that's mostly past us. So I'll tell a little bit about my background, just a few spot projects, and then we'll move on to the seminar. And just so I understand a little better, how many here are electrical engineering students? Okay. How many are graduate students at PhD programs? Okay. And how many faculty do we have here? Okay, the faculty mostly over here and here. So anyway, thanks so much for the warm welcome, and let's go ahead and get started. So an early influence for me was kind of like, maybe it's a passion for physics, but when I had a job as a 14-year-old pulling wires across a vineyard, you know, as the plants come up, they're very small, and I had to pull wires across and then tack them up on a post, and eventually would tack them on all the posts, and the vines would grow up right around the wires. Well, what I did is I was about on a kind of a hill. I moved the wire, and I saw the wave go down and almost disappear, and then it hit a tack on a post, and part of it came back, and part of it went forward. Well, that's interesting. Part of it came back, part of it came forward. So I did it again. My boss didn't fire me. I guess he didn't notice I was doing that, but I was doing vineyard wave experiments, and I thought, well, maybe when I go to school, I'll study waves. So I went off to Cal Poly and studied microwaves. Got a job at Hewlett-Packard working on W-band, super high frequency mixers, and went to work in the, I guess in the R&D lab there doing that. And then I felt I didn't quite have the theory I needed to continue my interest in the physics of waves. So I went and got my master's degree at UC Santa Barbara and studied microwaves and optics there, which sort of got me into optics. So I went back to work and helped lead the efforts for new light wave measurement equipment that was going to be used to measure internet communications, the photonics signals in communications. Then again, I was working on interferometer, which I'll talk a lot about today. And I didn't quite have the theory again to fully understand what was going on inside that interferometer when there's a laser illuminating it. So off to school again, this time Paris, because there was an article in the Journal of Quantum Electronics that the professor seemed to understand a related problem, and he understood the theory and the experiment. I thought, that's where I'm going to school. So that's how I ended up in Paris, not too far from the center, a very, very lovely place. So left school, went to HP Labs, beautiful building up on the hills with the trees. If you've been to Palo Alto, there's Page Mill Road. It's just up towards 280, a little bit out from all the venture capitalists and all that. And got my job there at HP Labs and started working on one project, do a spot check on it. It was a new kind of laser. It was called an up-conversion laser. At the time, there were not visible lasers readily available that were low cost. And so the idea was you have this heavy, this glass, called Z-band glass, that if you pumped it with invisible, longer wavelength photons, you could kind of climb up a ladder in energy and then create a cavity that would emit in the blue, the green, the red, and these wavelengths that were more expensive at the time. So I had a hand in that, literally. There's my hand. And another thing was coming along is we're setting the stage for the internet, global internet. And that was, how do you transmit internet signals from San Francisco to Edinburgh or other places? And so we do it optically, right? But as the signals go down that optical fiber, they slowly attenuate. So we had to build amplifiers, right? And amplifiers, actually, at the University of Southampton, they developed the first erbium-doped fiber, which was used for amplification. Well, you have these amplifiers, now they're degrading the signal due to noise, and so we need to establish noise figure theories and measurement methods. And so that was another project I had as a researcher there. Then finally, the mouse. So, you know, I became a project manager, and one of the projects I directed was a laser mouse. Well, you know, you wonder how all this happens, this lasers, everything. So I'll get to that a little bit later. But I also proudly want to talk about my relationship with the University of Edinburgh. You know, working with Dr. Chitnis and others, we've made a lot of differences in the laboratories. And so now the students, when they go in the laboratories, they have modern equipment to work with. And here's some recent pictures that were taken, you know, from that. So just lovely equipment, and that will help with their theoretical training. So let's get on to the exciting world for me, optical interferometers. And you know, everything I talk about applies for microwaves as well. But for me, it's just absolutely fascinating how you can measure the tiniest things and the biggest things with these interferometers. So anyway, let's delve into that. So lasers and interferometers are changing our world, all right? They're being used in robots and autonomous vehicles because they can measure things in 3D. So they're capable of capturing scenes in 3 dimensions and then taking that data and feeding it into engines that determine awareness, scene awareness, and so forth. And these will be used for food delivery, all sorts of things, rescues. And so we're just at the very beginning, I think, of this revolution in terms of autonomous vehicles. So even lasers in mice, as I mentioned. So how did we get here as humans? Well, I kind of look back in history a little bit. Everyone's heard of Ra, the king deity in Egypt. Around the 25th, 26th century BC, the Ra was getting very popular. And there's some artwork that was generated that kind of captured my attention because it pointed to early understanding of optics, right, at that time. And this is 10th century BC. And you see that actually the concept of a photon is there, which is interesting, you know, coming from the sun. You see directional properties, and you see also colors. And so early, us at an early age, well, you know, a couple centuries ago had an appreciation. Now moving forward to Isaac Newton, who I regard as the most brilliant scientist of all time, in my opinion. He came along and showed that white light was composed of colors. And he actually took those colors, separated them out, and then recombined them optically into white light again. So he could synthesize white light from the colors. He also brought the notion of dispersion. So for those in electrical engineering, you understand that. It's basically different colors of light travel at different speeds in a medium. And when that happens, then you get things like prism effects and so forth. And because he understood dispersion, he now knew that glass lenses were not the best lenses for telescopes without correction because of the dispersion. Different colors would get focused differently. And so he invented the refracting telescope, which eliminated the glass lens. He also coined the word spectrum. So whenever you hear spectrum, that was Isaac Newton. And for those who struggle in calculus, he's the one you would blame, right? So anyway, great person. Then, how many have heard of Michelson? Roughly 10, 20%. So he did what's called the ether experiment, and he developed his own interferometer, which we call today the Michelson interferometer. The Michelson interferometer was going to show the ether, and the ether is that medium that exists in space that electromagnetic waves propagate through. Just like water waves propagate through water, electromagnetic waves had to propagate through some medium, right? So all those scientists were convinced that it was the ether. So he built this interferometer, and with the ether, if there's a directionality of the ether, that should show up in this interferometer, which I'll explain the interferometer details a little later, but it should show up as a misbalance in the interferometer. So he built the interferometer. It was floating on liquid mercury, very stable, and he spun it around. He was going to see the ether, basically. Well, guess what? He didn't discover an ether, because there is none. So none that we've been able to detect. So anyway, he got the Nobel Prize for the work he's done, well-deserved. And it's also called the most famous failed experiment, because all the physicists knew there was an ether, and he was just going to prove it, right? Wasn't there. So interferometers, after Michelson, there's a bunch that came along. In my simplistic thinking, it's just taking optical fields, splitting them somehow, and then delaying components, recombining. That equation I just wrote up kind of describes that. So you're just splitting fields, you're recombining, but it does a lot of magic. And I'll talk about that magic. But it was the laser that came along that really caused the interferometer to shine. Because before you had these kind of tungsten lights, these broadband lights, but the laser with its single frequency hum to it, that made a revolution. And we can thank Dr. Maiman for that, as well as others who helped pioneer the concepts. But he demonstrated the first one. So now we have a laser and interferometer combined. That, to me, is the transistor of the sensing world, this combination. And we'll talk about that. By the way, that picture was done by DALI. That was a rendition by this new ChatGPT technology. That's what a laser looks like, anyway, to DALI. So laser basics, bringing up the speed on that. So a laser typically has a cavity. So there's two mirrors there that you can see, left and right mirrors. There is a gain section. In this case, I show 4 gain sections for, just to understand the concept. There's a pumping mechanism that's going to pump energy into the system, and that's going to be photons or electrons, current, electrical current. So that's going to pump the system. So now we have a resonant cavity formed by the 2 mirrors. We have optical gain, and so a spontaneously emitted photon starts reflecting back and forth. And it's going to reflect back and forth and reinforce itself as a result of that cavity. And when the mirror losses are such, I guess I should say the mirror reflectivity is such that there's enough photons coming back to overcome the loss and get amplified by the gain to repeat the process, you have a laser. And that's basically, you see a lot of complex lasers on benches and so forth, but basically that's what they are. Just a gain, a pair of mirrors, and some pumping mechanism. There's a lasing threshold. And so typically you'll see something that as you increase the pump power, not much power coming out. You hit threshold and all of a sudden, bingo, stimulate emission, lots of power coming out of the lasers. And they will resonate or oscillate at one of the resonant modes of that cavity. That happens to be also an area of wavelength where there's gain in the cavity. And so it lays there, and that sets the laser wavelength. Importantly, for interferometers, we talk about line width. So line width is how wide is the laser. If you looked at it in the frequency domain, imagine like a 60 hertz hum, a pure hum at 60 hertz. But if you start adding noise around it, you start getting other frequencies, then the line broadens. So it's no longer a pure tone. Well, this happens to be at 200 terahertz, but same idea. So the laser line width is inversely proportional to the power, roughly. So if you want a narrow line, you increase the power. Now, why would you want a narrow line? Well, for interferometry, the narrow line means that it has what's called long coherence length. And coherence length refers to physically, if you had an interferometer and you took a signal and you delayed it by much longer than the coherence length, the other wave coming would be completely incoherent. The phases would just wash out. There's no phase correlation between them. And so for interferometers, it's very key to understand what that coherence length of that source is. And so this is critical in interferometry. So lasers range from microwatts levels. For the laser mouse, I think our levels are around 700 microwatts to make them eye safe, to 500 trillion watts, like what you would have in the National Ignition Facility, right, in Lawrence Livermore. Tremendous amounts of power there. Sizes are of the order of 100 microns. That VCSEL, which stands for vertical cavity surface emitting laser, is an El Cheapo laser. It's a very good laser that's used in laser mouse. And it costs, you measure it in cents, the cost there. Gas lasers, I think everyone's seen them in Hollywood movies. Liquid lasers too, where liquid is pumped through a cavity. That's the gain media I talked about. And then the solid fiber laser in that example there that I showed. There's been a revolution in the last couple of years in lasers, and this, I think, will have dramatic influence on the application of interferometers in the kind of applications that we can envision today or tomorrow. And that is, you see the line width on the vertical axis there? And you see that line width has been dropping. You know, these are different type of lasers, DFBs, distributed feedback lasers, just different laser types in semiconductor. But you'll see an inflection occurring around 2015, 18, where all of a sudden that line width starts dropping. And that was due to the advent of our photonic integrated circuits with very low loss waveguides. They happen to be called silicon nitride waveguides. So these new waveguides permit the very, very narrow line width. And recently I heard about 1 hertz line width laser. And for those who have been in optics for a long time, that's astounding. So you have a carrier at 200 terahertz and a line width of 1 hertz. So think about that and think about the coherence length, right? 1 hertz, it was 1 over delta nu, so 1 over 1 hertz times the speed of light. So coherence length of 300 million meters. So anyway, I expect there's a revolution here going on with that kind of laser. So interferometers, I liken to kind of like a railroad switchyard where you have these trains coming that could carry hundreds of megawatts, right? Megajoules of energy. And a little kid literally can change the course of those trains. They can switch that power. So the trains are the photons, and then the switch is the interferometer. In terms of an analog for the EE students here, you can think of it as sort of like a transistor where the voltage at the top, the common collector voltage, is the laser power in the interferometer. And the small signal that would be used to control that transistor is controlled by frequency, gravity, acceleration, distance, and other things that we're sensing with that interferometer. And then you get a big output from that. And so that's kind of an analog. Now we'll jump into the laser interferometer parts. Very straightforward. Laser comes in. You got two mirrors. Upper mirror reflects the light back into this beam splitter. The mirror on the right reflects light back too. So you just have two reflections. Remember, it's just delay and recombine. So that combiner there then recombines those signals. They fall to the detector. And what we get out is really fascinating. You get a sine wave out depending on the phase relationship of those two arms. Why is it a sine wave? Well, yeah, to me, fundamentally, you have 2 degrees of freedom in the system. So a sine wave is like it's a fundamental basis function. So you have a sine wave there, but mathematically it turns out that way too if you derive it. So it creates a sine wave with that phase difference on that interferometer. Very critical for all the measurements I'll talk about. When you're beyond the coherence length, right, which is 1 over the line width times c, then when you combine these lasers, or the signals in the beam splitter, it doesn't really matter what that phase difference is, does it? Because they're out of phase, they're completely incoherent. There's no phase relationship that's governed, that's fixed between them. So you get this blob coming out, and that's the lower graph there on the right. That's the blob. And so that's the incoherent case. So that's your basic interferometer. It's just kind of forms like this frequency filter. It has a sine wave, and that sine wave then we're going to use in our experiments. So in terms of the fields in an interferometer, we have an input field shown as En coming in, and you'll see actually on the left there a diagram of the phase. And so when you get 180 degrees out of phase, right, 2 waves will cancel, right, because they're 180 degrees out of phase. So think of that interferometer then as the field coming in. It's split into 2 paths. For those in electronic engineering, there's a 90 degrees phase shift on that one path and 0 on the other, often. It can vary, but there's power conservation rules there. So you have 90 degrees and 0. So now you go to the combiner, and that through path is 0 degrees again, right? But that coupled path from the lower path coming up to the right, that's delayed by 90 degrees again. So you have 90 and 90 and then 0. So what happens when you combine a wave with 0 degrees and one with 180? And I'll have the electrical engineering students answer that one. Huh? You get cancellation? You say cancellation? Yeah. So they cancel each other out, right? They're 180 degrees out of phase. So you get one port that has nothing out, and that's how one of the interferometers, the LIGO interferometer I'll talk about, that's how that works. Nothing coming out of that port. The lower port, you have that 90 degree split, and it goes through a 0 degree split, 0 degrees through the combiner, so it's just minus 90, right? And the other was 0 and 90, so it ends up being minus 90. So you're adding a minus 90 with a minus 90, they reinforce, right? So that's the basic physics there. And so what happens if you delay one of those arms by just 180 degrees? And I'll say 180 because it sounds like a big number, but it's a really small number in terms of sensing. Well, now we've completely flipped them. So now the upper port, as you can see on the curve on the right, it's got output signals, the lower one doesn't. So with just 180 degrees phase shift, we completely switched the tracks. We completely switched the energy. And that energy could be hundreds of megawatts flowing through the system, and we just switched it. So what does it take to impart 180 degrees phase shift on an optical signal? Well, let's pick a blue-green light at 500 nanometers. That's the wavelength. Very, very fine. 500 nanometers for one wavelength, so half wavelength would be 250 nanometers. So with just 250 nanometers of shift in that arm, I can completely flip the power from one end to the other. So very small signal. So that's the basis of the interferometer. So my first interferometer I built, I was using actually the Michelson interferometer there, and the goal was to see what the laser is doing under modulation, because all this internet modulation, the ones and zeros, modulating the lasers, they modulate the power, but they also modulate the frequency. So how do you make a measurement with that? Well, it's a sine wave. So what if I park myself at what's called the quadrature point there, an interferometer, it's kind of the midpoint of the output power. And it turns out that scaling, it's not theta now, it's frequency, but omega t and theta are the same. If I have a frequency change on that laser due to that modulation applied, it's now causing us to move around on that interferometer curve, the linear portion of that curve. And so it converts it to intensity on the output. And so that red curve on the right is what the discriminator is saying that frequency is, the laser is doing in terms of frequency during the modulation. And that lower yellow curve is just the intensity modulation the laser is going. So you can see that even though you're modulating the power to communicate, you're also modulating the frequency unintended. That combines with dispersion that I talked about earlier. Different frequencies go in different speeds, and that turns your square waves into blobs. So very critical for measurement. And then also, I said, well, what is the spectrum of this laser? In other words, if you want to find out what the frequency components were of that modulation. Well, we didn't really have any high resolution methods that were convenient at the time. So I developed this interferometer. I called it a gated delayed self-harmonizing interferometer. And basically what it did is it says, hey, I know the coherence length of my sources are of the order of 5 meters, something like that. If I delay the waveform, I separate it, and I delay one path relative to the other, they're now incoherent with respect to each other, and I'll call this one a local oscillator. I'll recombine it, and it's like a local oscillator mixing with the modulated signal. It's like a radio receiver. You get out a spectrum. And indeed, we were the first to measure the FM spectrum. If you look at that, it looks kind of like an FM type spectrum of a laser that's modulated. And now we know exactly what the amount of frequency modulation created and, of course, spectrum broadening. So that was my first patent, actually, my first publication was that. Now, the interferometer for life sciences, chemical analysis. So how many have heard about Fourier transform infrared spectroscopy? I see some nods. Okay, 5%. So this is a revolutionary interferometer and what it's done for mankind. Behind the scenes, you may not know it, but it's done so much for analyzing chemicals. So what is it? It's an interferometer again, just like we had before. Light comes in from the side, but this time it has a moving mirror. So that mirror is moving back and forth. So you remember that sine wave I showed that you get with position? So at one frequency, in this case, let's say we had a broad input light, and one frequency was at 10 micron wavelength. That's infrared wavelength that you can't see. Well, as you move that mirror, you get a sinusoid, because that's what the interferometer generates, right, when you move phase on that interferometer. Well, what happens when you're at 5 microns? Again, a sinusoid. And at 1 micron, lots of sinusoids. And half a micron, even more sinusoids. So how many have had a Fourier transform? Most everyone, good. So what happens when you take Fourier transforms of an aggregate of sinusoids? You get all your spectral lines, right? So now we have a spectrum. That's the Werner-Kirchheim theorem. But you now have a spectrum here, and superimposed on that spectrum is the absorption of that chemical that's being absorbing thing versus wavelengths. So now we can identify chemicals, specific chemicals, based on these absorptions, which happen to be related to the vibration spectrums that those chemicals have with their chemical composition. Huge business here around the world today. Following similar ideas, we developed the first coherent optical spectrum analyzers that were commercialized. Again, interference between a local oscillator and a signal much like a radio receiver. You tune the laser, you sweep the laser versus frequency, and at the point in frequency sweep where it lines up with the frequency of the signal, your detector detects it, you detect a line, and you get a spectrum. Now, to compare with classical technology, that blue line there represents classical grating-based spectrometers. Gratings have been around forever, right? You shine light on it in the different colors, disperse, angular, and you can filter it out. With this, we're 1,000 to 1,000,000 times more resolution than you'd get with classical technology. So once again, interferometry to the rescue. Now I want to jump to LiDAR, like that video I showed in the beginning, the Velodyne LiDAR. So LiDAR, once again, what do you think it's based on? Anyone say interferometer? That is an advanced method that's being used, one of many, but the interferometer now, the laser is just changing frequency versus time. You can see it on the left there, changing frequency. It hits a mirror, and then goes out and hits a palm tree. So, and you can see there in the upper right path that what's called a local oscillator versus time is changing in frequency. So what's going to happen when it reflects off the palm tree? It's going to be delayed in time, right? That ramp is now delayed in time. So what happens then at some point in time, like where that delta F is shown, when that signal goes back to the detector, it now has a signal called delta F, right? It's combining one frequency with a delayed version of itself, and it creates a delta F. And you can see from the diagram that that delta F will depend on delta X or delta T, how far away the palm tree was. If the palm tree was right next to it, it would be very short and you wouldn't see much frequency at all. So that's how the LiDAR works, based on what's called frequency modulated reflectometry. And you can see that with that you get 3D representations. Not all interferometers have to be coherent. There is one called the low coherence reflectometer that we had experimented with for a while and actually turned into a product. And that one is based on the fact that, remember before we had coherence? Well, what if you had a very short coherence length, close to 0 microns, very, very short? What happens when you get a signal that goes out, say from one path, and it combines and there's a delay that's beyond that coherence length? You get nothing, right, the noise. But when they're exactly aligned in time, those two reflections, you get the signal, basically. So there's an ASE source, amplified spontaneous emission source, which is a bunch of noise. It goes to the coupler. It's hitting a device under test that we want to characterize the reflections of. And the power goes back to the light detector. You can see that that won't work, right? Because we'll just get a blob of power going out. But what if we add another arm to make it an interferometer, and that interferometer now is going to have a mirror that's going to displace in time? When that mirror lines up to any one of those reflections, the path length is identical between that dot path and that lower mirror path. When they're identical, you get interference and you get this blip. All of a sudden they're coherent. And so that results in basically a measurement of reflections in an optical device. And you can see it there on the lower left. So we measured what's called a Rayleigh backscatter in glass. Rayleigh backscatter is due to, in the glass anyway, as the glass cools down, there's going to be slight inhomogeneities in the refractive index, very small. This technique can actually measure that. And those are two different fibers with two different levels of that backscatter. And we looked at the case of a fiber end, and we said, how far down can we see in terms of those reflections coming back from the Rayleigh scatter in the fiber? And it was astounding. It's a minus 148 dB. Does anyone have a sense of 148 dB? I don't. I mean, it's such a huge number, right? I mean, something 148 dB down. So I thought, well, what is it if you took people and you lined them up, right, and to the 10 to the 14.8, how far out does it go? It goes out to about 50 times the distance of Pluto. And so it's just humongous, the resolution. So we had some world records there, some interesting results on low coherence reflectometry. So how did the laser get into the mouse? Kind of silly, right? You think these lasers are expensive, right? Well, the LED mouse we had, and our lab had invented what's called the optical mouse. It was facing the problem of copies were being made around the world. And so our partner, Logitech, said, well, you know, I was at Agilent at the time, you guys have to can you come up with something that's differentiating, right, to deal with these copies? So we looked at current mice technology, and we looked at what I call a surface spectrum. And you can see on the left the surface spectrum that has everything from white paper to Tommy mats, all the way across whiteboards. And the ranking of the mice is the vertical axis. So a good mouse has rank 10 all the way across all those surfaces. You can see that the optical mouse, as good as it is, had a lot of shortcomings. Tatami mats were like an issue in some parts of Asia. Whiteboard didn't have much contrast. So if you used a mouse on a whiteboard or a surface like a whiteboard, it wouldn't be able to navigate very well. So we found these issues, right? So we thought, well, what can we do? And so I led a bunch of brainstorms. I got the smartest people in the labs I could get. I said, okay, mechanical engineers, optics, physics, come up with ideas for a better mouse. I didn't say laser mouse because we didn't know at the time. So some people actually had ideas where you pull a string, right? I mean, we had everything. No idea is a bad idea when you brainstorm. And so what came up was this idea of shear interferometry. And Tong Shi came up with that idea and says, well, maybe this if we try it. But it wasn't clear at the time that that was going to be a radical breakthrough. It wasn't clear. And so we ended up developing that idea. And what a shear interferometer does in a nutshell is it converts surface shapes. It takes derivatives of surface. And so by virtue of basically taking beams and delaying them in space, creates derivatives in that space. And so you can get a output image that's a derivative of the surface. And so any surface features, derivatives are always kind of like amplifying changes, right? Get converted into the images that we see instead of a kind of a blah image. And so that on the right is images that you get with a shear interferometer. Operate in one direction, it creates this derivative. So we entered this mouse competition, by the way, with this. So here's the world's first demonstration of a shear interferometer mouse, laser mouse, working off of a whiteboard that you can see there. The laser comes in, bounces off the whiteboard, comes off the whiteboard, hits a little shear interferometer that you can barely see, and then hits the camera that's taking a picture of the image. It worked great. And so if you compare that image to what a mouse, LED optical mouse would get, you have the LED mouse on the left, right, that's busy taking pictures of the surface, doing correlations between them, trying to figure out which way it's going. Well, the image on the right is far easier to navigate, right? It's not like a flat desert. You have hills and things to look at. So it was about, we advertise as 20 times better than optical mouse. And the first laser mouse is that one there, that brick we call Quattro, because it can go on a lot of surfaces. So we entered this competition against 5 other technologies, and we won, otherwise we wouldn't be talking about it, right? So anyway, it was a special evening for me when I saw Jack Winstrand, the CTO of our business unit, that was responsible for commercialization. He left me that note. And what do you think fasten your seatbelt means? Well, Jack knew that I was in the scientific instrument space, electronic test equipment, right? This is consumer business, and you had to hit the Christmas buying season in August, right? You had to do these deliveries. So it had to go extremely fast, and it did. And at that point, I don't claim any connection, because once you bring in hundreds of people, manufacturing experts, materials, supply chain experts, tolerance analysis, statisticians and all that stuff, it's a huge train, right, doing the commercialization. And that's where the big investment is. So it turns out our Quattro mouse, if you look at that red line there, had much better performance, right, than the mice. And that resulted in, Logitech was very happy. We transferred it to Logitech. They do all the huge company, right, worldwide distribution. So they took that from our prototype. We developed Herbie. Remember Walt Disney Herbie movie? Anyway, Herbie developed the prototypes and then production samples. They started about 5,000 at a time, and then you go up to 50,000 unit lots. And off to Logitech, and it became the MX1000. Now, what do you notice about that package that is kind of interesting? Does anyone see it?
Says laser.
It says laser, yeah. And what else does it say? Right below laser. Maybe the print's kind of small. Does it say, I think it says optics is obsolete. Which, from a laser guy, optics is obsolete, but we got laser. Okay, well, anyway, that's marketing folks, right? Bless them. So anyway, first project I worked on, I think my family understood, right? Finally I did something useful. So anyway, that was a great project. So lasers and interferometers are everywhere, right? You saw it in mice. Now in communications, they've really taken off. So in the, I guess, old days, and to a certain extent today in data centers, you communicate information by ones and zeros, right? Ones and zeros are communicating. It's like a toaster, heat, no heat, neat, so you communicate in digits. Well, to cram more information down the optical fiber, they've gone to what I think is just degrees of freedom that they have in that fiber, right? So you can work in polarization, right? This polarization or that polarization of light. You can work in the amplitude of the light, much like we do with the ones and zeros. And you can work in frequency and phase, all those. So the diagram on the right gives an example where we're looking at kind of constant amplitude, but you're changing the phase of the signal. And you're changing it relative to some clock, let's say. So there's some clock and you're changing the phase. So as you change the phase, you can encode information. This phase is a 1, 0, 1, next phase is a 1, 0, whatever, however you denote it. So you now, with phase, are getting information down that fiber. So when you look at in terms of degrees of freedom then, on the left I show some equations, says EX, EY. Don't pay attention to EY, it's just another physical direction. So if you just look at EX, we can change the EX amplitude, right? We can encode information on amplitude. We can change the phase that I talked about of the signal. And then looking at the right-hand side for the case of just X polarized optical communications, you can see that how far away out you are from the center, that's the amplitude, right? So you're encoding amplitude with all those little dots. And then the angle with respect to the horizontal axis is the phase. So now you're encoding in phase. So you've got 256 points now, right, to work with. And so you're sending a lot more data now with every symbol down the line. So that's used because we were running out of fiber capacity. So we needed to get more, basically more communication bandwidth down there. And so how do we detect that? Well, once again, interferometers are to the rescue. Here we're interfering a laser local oscillator and receiver with different delayed versions of the signal. And from that, and I don't like throwing a lot of equations out, but if you look at the lower equations on the lower right, we have some unknowns. We have AS, the horizontal amplitude. We have delta phi in the second line, that's the phase. And then we have both for the next two or for the other polarization. So you have 4 equations and 4 unknowns, right? The amplitudes and phases, and we can compute it. So Keysight actually came out with a product in this space that's used to measure these communications, these high-speed communications, terabit communications. So I talked about bulk optic interferometers. Now I want to show how interferometers can get small, for tiny little things. And so here's a project that we had with UC Santa Barbara, where now on a single chip, a very small chip, it's measured in a couple millimeters. We're combining lasers together, 2 lasers on the left, coupler in the middle. SOA stands for semiconductor optical amplifier. We amplify and we detect on a photodetector. Now you have 2 lasers that you can tune. They're combined together, so now you can make a microwave or millimeter wave source, right? Because you can tune the frequencies apart and measure on the detector. So this is all possible due to light guided by what I call index wires. So instead of copper wires guiding signals around on an IC, use index changes, and they guide signals around. And so they're guiding the optical fiber around. So it's called a PIC, photonic integrated circuit. Here's a picture I took about a week ago of some ICs, PICs at UC Santa Barbara. And you think, well, it's on a tiny little circuit, so how can you get a large delay if you need one? They've got delays on there due to wrapping these index-guided waveguides around 10 meters or so. So it's huge changes. So with these tiny interferometers, you can now do drug studies, right? So what if on that interferometer on that chip, what if I functionalize the material, which means I put some sort of molecules on there that attract certain drug molecules, let's say. They attract certain molecules and not others. So what happens then, that with this functionalized surface, you're testing all these chemicals, when something adheres to it, you got more matter on that section of the interferometer that it's adhering to. And you can see on that right, the sensor surface there. So now it's sucking up these atoms, these molecules. What does that do to the index refraction, the optical index refraction? It's going to shift it because there's more matter there, right? So index refraction is matter interacting with light. So now you've changed that on that interferometer, you're at quadrature. All of a sudden these drugs start attracting there, more matter, you shift the phase, and now you have a measurement of the amount of matter, hence drug, on that surface. So now I'm going to get to really fun stuff, really big interferometers. Large interferometers used for gravity wave detection. Has anyone seen the simulation, by the way, that was done? It's a great simulation. The reference is down at the bottom. You can see there. But great work on simulating black holes, right? And how they come together and form one. So everyone's heard of LIGO, the Laser Interferometer Gravitational Observatory. I always call them. Now we're looking at a 4-kilometer path length. There it is. So what does that look like? It looks like an interferometer to me. It is. So you take this interferometer, you send light down 2 paths, and now the mirrors are dangling by silicon wires that if there's a gravity wave that comes through, it's going to shift it slightly, those mirrors, highly polished mirrors. You feed a laser into the system, and now you're looking for changes in phase on the output. So in this case, they operate a null interferometer, which means on that diagram I showed you, you're operating at the bottom where at the detector there's no light at all. So any slight shift in phase on that interferometer, which is millions of watts, will cause us to go from 0 to something. So you have LIGO built up in Hanford, Washington, and then one day they see this little wiggle. They go, wow, that wiggle, it looks like a black hole wiggle. But how do you know it's not a truck going by, right, with a driver whistling? So they don't know, right? But they built 2 LIGOs, right? And so in Louisiana, they have another one that detected the same wiggles, but 7 milliseconds earlier. So they detect in Louisiana, and then later they detect 7 milliseconds later in Washington. And they agree. And so that was the Nobel Prize winning measurement of detection of a black hole event. That's those swirling black holes combining to make a measurement. Now, for me, it's fascinating that the light took 1.2 billion years to arrive at this interferometer. 1.2 billion years ago is when this happened. When it arrived, it caused a fluctuation space of 10 to the minus 18 in terms of meters, right? So how do you measure 10 to the minus 18 meters? Well, really smart people there, but one thing is, remember the amplitude was power? You crank up the power into the megawatts in those interferometers. and that allows you to get the sensitivity needed for that measurement. So it was really a breakthrough in power and instrumentation. Now we're going to go into a really big interferometer. Has anyone heard of Grace follow-on? Okay, well, you've seen it. I had a chance to talk to some of the people that worked on this. It was fascinating work that they did on this interferometer. So now you have an interferometer, and you can see it there. There's a laser in the lower bottom. It's splitting the red line out, and then there's a blue line coming in. Once again, you have interferometer with path lengths of 200 kilometers now. So it moved from 4 kilometers to 200 kilometers. They're going to make measurements of gravity. And so they package it all up, they ship it out in space, and I have a great video here that they did that describes this experiment. So we'll put it on here.
Water is one of the main indicators of how the planet is responding to our evolving climate. We built our civilization around the climate that we had and the water resources that we had. And if those are changing, that can have a profound impact on how we operate our society.
GRACE and GRACE Follow-On measure the motion of water around the Earth, and they measure that in all forms of water. Water that's stored underground, water in the ocean, water that's frozen in the form of glaciers. So all of that together, GRACE can measure.
GRACE Follow-On is a mission to measure how water is distributed on the planet and how that changes from month to month.
GRACE stands for Gravity Recovery and Climate Experiment.
And it's a follow-on mission to this mission called GRACE that we launched in 2002. And that mission just ended a few months ago, and GRACE Follow-On is going to pick up and continue that science legacy.
So even though GRACE flew for 15 years, climate is one of those things which takes place on decadal timescales. It's really important that we look at these trends over longer time periods so we can establish the forces which are driving them.
One follows the other, and between them they accurately track the distance between the two satellites. And as they fly over changes in mass on the Earth, they move back and forth. And we track those little changes very accurately. And we do that with global positioning system satellite information and with star cameras that are on board the two spacecraft. I think there's an increasing awareness and consciousness around the Earth that water is a critical resource, and that the sea level is rising, the polar caps are melting, and that all these have long-term ramifications on how we live.
The GRACE follow-on measurements give us very clear and tangible information so we can make sound decisions in the future of how we manage our resources.
Just love that video. Now we talked about a very large interferometer, right? Now we're going to talk about a huge interferometer. And this is LISA. It's a laser interferometer space antenna for black hole gravity wave, long wave detection. So the earlier LIGO could detect shorter period black hole radiation because the arms are shorter. But if you go to really long path length difference in the interferometer, then you can measure even longer wavelength gravity waves. And this one is astounding that this trio of satellites is chasing the Earth around. It will, hasn't launched yet. Separated by about 15 million miles away from Earth. And the arms now are 2.5 million kilometers. 2.5 million kilometers is twice the diameter of the sun. That's how far apart these are. And this will launch in 2037. So, that is going to be the biggest interferometer. I can't say in the world because it's not in our world anymore, in the solar system. And so that'll be exciting to see what they find in terms of black holes and our understanding of nature. So I'm going to get into, I've got a couple minutes, and I'm just going to throw out something provocative to you. Especially the physicists in the environment, in the room here. Has the speed of light ever been directly measured? No. And that's the exciting thing about where we are in terms of there's so much mystery in this universe. Michelson did a super measurement where he took light from one mountaintop, shone it on a mirror on the other side, and it came back and it hit a rotating mirror. When that rotation was just right, in other words, if that mirror was still, you wouldn't get any light out of the detector, which was his eye. But when it rotated a certain amount at a certain speed, you could then see light reflected from that distant target. And so from that, at 528 RPM and the distance, he was able to determine the speed of light going there and back, but not the speed of light going one way. And for those interested, Versatility has a great video actually on this topic. So that got me thinking, well, speed of light, I think, Einstein said the speed of light I can assume is isotropic. And Michelson said, I measured the round trip speed. But, in terms of possibilities, light could go slow one way and then fast the other way. That's time on the vertical axis, space on the horizontal axis. There's lots of possibilities there, right? And so I was thinking about this and I think, well, maybe an interferometer can help out here. And so came up with a concept that I call the Crow's interferometer. It's counting reflectometry for a one-way speed of light measurement. And the idea of this interferometer is that it doesn't measure return time. All it measures is the existence of a photon that hit a surface. And so we establish, when you have simple diagrams like this, right, you only need two boundary conditions, right, to solve this system. So you have the one where you're starting at x equals 0. You have your clock. Okay, that one's set. I have a clock and I have a point in space. You just create another boundary condition which defines a space-time point. Well, how do you get that space-time point? Well, the idea then is to use reflectometry to probe that space-time point which changes at a certain point in time due to a calibrated mass that traverses that distance. So I presented this in Pasadena, with all the JPL people and all that. And one person marched up to me and says, the speed of light's the same in all directions, and then he turned around and left. And I said, I think it is, but has it ever been measured? That's all. That's all I'm doing here. I'm not threatening the dogma. I'm just saying, can we measure it? So here's the idea then. You have this calibrated mass that shoots across, and we're going to use that, a massive object, which is going to traverse from A to B, and that's going to be our calibration, and that's going to change the boundary condition at point 2. So the way that looks kind of in optics land is you have mode lock laser, it's sending out this series of pulses, and those pulses are going to bounce off a mirror at the other end. At a certain point, that mass is going to break the mirror, conceptually. It's going to break the mirror. And that breakage of the mirror defines that second space-time boundary condition. And so you see we're counting return photons, but not how long they take. They could, as long as it's shorter than the measurement. So you'll see that green photon is the last one that hit the mirror before the mirror broke. And that is the magic one because that allows us to calculate basically the speed of light. And so that's the concept, and the math is very simple. It creates a triangle. You have that green photon, which is the last one to land on that mirror before it broke. You know what the distance is, and then from that, you can calculate the speed of light. So that's the idea. Anyway, a little bit provocative because it does go against current thinking that we just assume that light's the same in all directions. And I hope one day that we'll be able to do an experiment to try this out in space with a long distance, right, and measure the one-way speed of light. So I summarize here that lasers and interferometers are magical. They make magic in terms of our ability to understand the world and do things. And it will continue to evolve. So if you're thinking about a career, there's a big career here, right? I mean, it's always, I think, for the next 100 years, is going to be revolutions made in this space. And anyway, quite excited about it. So I want to thank you for your attention, everyone online and here. And anyway, it's a pleasure to speak with you today.
Okay, thank you very much, Doug. So welcome everyone. I'm James Hopgood. I'm Director of Electronics and Electrical Engineering, and I'm going to give Doug a vote of thanks. So,
oh, my pleasure.
So that was an absolutely fantastic talk. It covered a really wide range of topics, which I wasn't expecting you to cover, starting off from the vineyards back in California, all the way to measuring the speed of light, but going through Paris, Sao Paulo, designing the laser mouse was really exciting. And the thing that I took away from it was not only all your scientific contributions, but the impact that you've had in industry, the impact that you've had on all our lives through the products that we're using, or if we've not got laser mouses, we should get some as soon as possible. But I think for the students in the room, I think you should be inspired by what Doug has done. If you look at the career trajectory that Doug mentioned at the start, then it sort of showed that straight after graduating in EEE, he really got involved in areas that was making a major impact. So I think for the students in the room, you should be inspired. And I think for the academics in a room, we should probably be a little bit jealous of some of the activities and start working harder, eh? So just on that note, shall we take some questions from the room before I say the thank you? So does anyone have any questions they want to lead off on? So we're going to try this red thing, so get your catching on.
You throw this.
Yeah, hopefully it will work.
Can you
I think it works. Ready? So, see how good my throwing arm is.
Oh, nice.
Okay.
So in terms of time frame, when was the first mouse? Like, I was just wondering while listening to you, when was the first mouse actually, laser-based mouse?
The first laser mouse? Yeah, that's a great question. And the reason is actually economics that forced us into doing that. I had a telecom team where we worked on packaging holographic demuxes and really cool stuff. The economy came along and wiped out the telecommunication industry. So that was around 2001. So we went off and started work on the mouse, and it was around 2002-03 is when that came out. So that's when the laser mouse. Of course, prior to that was the optical mouse, right? But that was the laser mouse back then. So it was quite a ride. The way I think of that project is, in this particular case, it's like there's a train going through town, you have an idea, you hop on it quick, because that manufacturing, all that stuff, worldwide, it's a huge inertial thing. And if they give you a spot to hop on the train, you do it. And so we got a little bit lucky that the timing was right for that.
Thank you.
Thanks for that. That was a really interesting lecture. I really enjoyed it. I think my question is, at the beginning of your career, did you have an insight into how far your work could go? Or have you always just sort of followed the path and the curiosity and now we're here?
Yeah, so how far would the work go? I really didn't have an idea of that. I had this vision in my mind that a doctorate is something I wanted to do someday. So, I even posted on my door in college, Dr. Doug, with office hours. And so I had that vision, but the way I ended up there was through opportunity that doors opened. Like this HP fellowship came up, and when the fellowship came up, I applied for it, and it allowed me to get my master's, right? So then I could pursue the passion of understanding waves a little bit more at UC Santa Barbara. Then after that, went off, and because of the new work I was doing with interferometers, which I didn't have the theory at the time to handle, I thought I need more education. And I came across this journal article in the IEEE Journal of Quantum Electronics. I go, wow, this professor knows a lot about that. I'm going to leave my job, right? It's kind of comfortable being in industry to a certain extent, right? Academia is actually very challenging. It's a lot of hard work. So I just said, okay, I'm going to go, and I'm going to Paris to get my PhD. So coming out of there, it created more opportunities. Hey, Doug, how about look at heavy metal fibers for lasers, upconversion lasers, and these new erbium amplifiers coming out. So you just pursue your passion as opportunities come up. So it's kind of like that. So it's just a product of humanity, basically. Yeah. So I don't know whether that answers your question, but I think if you see opportunity, take it. I guess don't close the door.
Thank you very much. Very nice presentation and talk. So I just want to ask, you have talked about different applications that use interferometers. Just want to see for future, which application do you think would be the killer one? What application that's, really interferometers would be the main aspects of the design? I mean, some of the applications that you mentioned, for example, when we go to astronomical imaging or even for optical fiber communications, typically, coherent detection is on the advanced side of things. But what application do you think would be the everyday kind of application for interferometers?
Okay, beyond the laser mouse.
Yes, beyond the laser mouse.
Every day. So one of the exciting things was, remember that curve I showed of laser line width versus time? So in relatively cheap, low-cost laser platforms, which is heterogeneous silicon nitride, this low-loss silicon, that line width going down to 1 hertz, traditionally those, and I was a microwave engineer, would say, oh, optics is dirty, right? Because the lasers have line width and they're always shaking around, right? So it can never do what electronics can do. Well, I think now with lasers getting down to 1 hertz line width, you can talk about these compact structures that can generate all sorts of electronic waves. And once it can do it better than electronics, which is always getting better, right? But once it can do that, it can touch off applications into the electronic space, which could be very diverse, all sorts of signal generation electronics. So I think that would be a major disruption. Certainly Lisa and LIGO and Grace Follow-on, those are great, but in terms of everyday life, there's only one of them, right, out there. So it's not huge. But I think that conversion of optics to electronics would be a big deal.
Sorry, just one follow-up question. That 1 hertz one, wasn't it with high power?
Typically with lasers, you want to do as high power as you can, right? But it wasn't like megawatts National Ignition Facility lasers. They were practical sources. But generally, you want to get as high a power as you can in the cavity, because any little noise photon, in terms of angle, is very small, right, relative to that vector. So a high power will always help there. And I know in Australia they're working with diamond resonators and things that can handle high power.
Thank you.
Yeah, great questions.
Okay, we've got a question over here. Let's go right me. Okay.
Thank you so much for sharing your wisdom. So I'm working in the AI field. My question is, as ChatGPT just demonstrated the power of AI, but as an AI researcher, we think this is just the starting point. Could you share your vision in coming 20 or 50 years? How AI, what's the next big thing? Combine AI with a sensor or sensing. Let's say a smart sensor. Could you maybe share your vision with?
Yeah, that's great. Actually, the talk title, I came up with a talk title, and we used to work at Hewlett Packard and Agilent. We used to describe our marketing at HP back before the printers and ink as selling sushi as cold dried fish, cold dead fish actually. That's sushi, right? And so when I was working on the title and the abstract, Dr. Shitness says, oh, let's try ChatGPT, see what it comes up with, right? And I was embarrassed because it came out with a much better, much more catchy, right, abstract than what I had, right? Mine was cold dead fish for sushi. And so this revolution that's going on in AI, as a scientist working in a field where the optics is getting incredibly more complex, the degrees of freedom expanding exponentially, it will help solve problems that we couldn't solve before. And so my expectation is AI will come in with software developers. It'll make one developer very powerful, right, using those engines. And it'll actually probably displace a lot of jobs. And I think in optical design, as we get to very complex systems, AI can help us solve topologies that we never even thought of. Not to the extent of what's called genetic algorithms and things like that, or random algorithms, but intelligent synthesis. So I see that coming soon.
Yeah, since the lot of like, for example, the event-based sensors, the new concepts, new paradigms comes, but from the technology in the lab and to the product or commercialization or working, product on the market, how long do you think that will happen?
How long till AI hits the market, hitting optics?
Yeah, the new concepts come.
Yeah, there's already discussion, I know, in microwaves, using AI to help with microwaves, where the human would come with a topology, and the AI would come in and solve the problem, things like that. So that those concepts are happening. I have not heard that in optics yet, but it's just a matter of time. And beyond the design, the AI can say, okay, we could create design, we could take sensor engines that are not really in the conventional way we think, but are capable of aggregating diverse data that comes out of this in ways that we hadn't thought of to make that design very beneficial. So, when we talked about microwaves years ago, we said W-band, which is 75 to 110 gigahertz, really fast. Oh, that market's just around the corner, right? It's just going to happen. And every year we heard that and heard that. Yeah. It was 20 years later that actually happened. So I hate to say put a date on that. But I would guess as fast as things are moving, within 10 years, we'll see products that are all AI assisted, helping with design and so forth. That's my guess.
Thank you so much.
But don't record that.
Yeah. Okay, brilliant. Any final questions? If not, Doug, so first of all, I'd like to say thank you again for a magnificent talk. But for everyone here, I mean, another big thank you is for the work that you've been doing with Daniel and with the school and with the college for outfitting our electronics labs. And the two pictures you had at the start of the talk, I mean, the Kivlin labs, as we call them, the electronics labs, have never looked so good. I mean, that looks really good. We're getting those photos broadcast as soon as we can. And I know, I mean, for example, we were very proud to show that industrial collaboration with our university provost when she came around to have a look at the labs. I mean, it's just fantastic that we were able to show that investment. So I hope that continues. So thank you for your investment on that. I mean, thank you to Daniel in particular for taking the lead on that. This started just under 4 years ago. Yeah. And Daniel in particular was key to driving that forward on behalf of the discipline and the school. And our head of school, Brody, took a big initiative to get the college invested and to matching that investment. So that wouldn't have been possible without you.
It's a great partnership.
It's a great partnership. So it's a real sort of exemplar of what we can do with industry. So thank you very much for that. Yeah. Also rounding up, I'd like to say thank you to the people who organised the talk as well. So Louise, Laura, Margaret and Chloe, who are outside, who have helped organise. And thank you to all of you for coming and supporting this event and asking questions. And I hope that you can hang around for refreshments afterwards and come and chat to Doug. And we'll be seeing much more of you over so in future. We'll see you back in the opening of the labs later in the year. So let's give one final thanks to Doug. Thank you very much.
Thank you very much. And I want to thank University of Dr. Chitness and everyone for how easy it's been to work with the university. And also thank everyone online for attending today. So thank you very much.